Professor Maudi.
Good afternoon, colleagues. On behalf of the Vice Chancellor and Principal, Professor Nanapoku, it gives me great pleasure to welcome you to the inaugural lecture of Professor Johnson Lin. The Vice Chancellor conveys his congratulations and best wishes to Professor Johnson Lin. Inaugural lectures form part of the university's public lecture series and may only be presented by newly appointed full professors who have been appointed in academic schools and centers. Inaugural lectures also present an opportunity for showcasing the exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in academics' career, their ability to provide official recognition of their promotion, as well as recognition of their appointment to full professorship. These lectures are furthermore an ideal opportunity for the new professors to introduce themselves and to present an overview of their own contribution to their field, to academic peers, to students, and research collaborators. Inaugural lectures are also a platform for celebrating a professor's academic achievements with his or her peers, family, friends, mentors, and colleagues. I would like to acknowledge the following guests: members of the executive management, members of Senate, our inaugurant this afternoon, Professor Johnson Lin, family and friends of Professor Lin, academics and professional staff, students, alumni, and distinguished guests. At this stage, it is my pleasure to introduce our Dean and Head of School, Professor Ademola Olaniran, who will now formally introduce the inaugurant, Professor Johnson Lin.
Thank you very much, Professor Modi, the DVC and Head of College of Agric Engineering and Science. Good afternoon, everyone, and thanks for joining us this afternoon for the inaugural lecture of Professor Johnson Lin. It's with great pleasure that I introduce him to you as our inaugurant for today. Professor Lin is a full professor in the Department of Microbiology within the School of Life Sciences, College of Agric Engineering and Sciences, University of KwaZulu-Natal, Durban, South Africa. He received his BSc fourth-year degree from the National Tsinghua University in Taiwan in 1984. He earned a PhD in 1992 at the State University of New York at Buffalo, United States of America, under the supervision of Einstein Professor J.H. Wang. He went further to pursue postdoctoral training on the structure and function of reverse transcriptase of HIV-1 under Professor J. Coleman in the Department of Molecular Biophysics and Biochemistry at Yale University before migrating to South Africa in 1995. Professor Lin joined the Department of Microbiology at the then University of Durban, Westville as a senior lecturer in June 1996. He then joined the Department of Biochemistry and Microbiology at the University of Zululand as a lecturer in 1997, before being promoted to senior lecturer in microbiology at the same institution. He was appointed as an associate professor in the Department of Microbiology at the University of KwaZulu-Natal in 2003 and was later promoted to a full professor in October 2020. Professor Lin's main research focus is on environmental microbiology and bioremediation. In recent years, his lab has utilized molecular techniques in exploring the potential applications of microbial enzymes. Over the years, he has published 121 research articles in national and international peer-reviewed journals in its areas of research focus and related topics. He has successfully supervised 11 doctoral and 90 master students and mentored 6 postdoctoral fellows. He is currently supervising 5 PhD and 3 MSc students. Professor Lin was a recipient of research grants from the NRF, WRC, MRC, and the Kronberger Foundation for the Faculty for the Future program over the years. He has served as an external representative on the selection committee and staff performance evaluation for the Department of Biochemistry and Microbiology at the University of Zululand. Over the years, Professor Lin has examined a number of MSc and PhD theses from various universities, including the Northwest University, University of Free State, University of Limpopo, University of Zululand, Rhodes University, Durban University of Technology, Bala Institute of Technology in India, as well as Nama University and University of Zimbabwe. He has served as reviewer and editor for different journals over the years. He is an editor-in-chief of the African Journal of Biochemistry Research since 2007. He is a member of the editorial board of Water SA, a member of advisory board of the International Journal of Biotechnology from 2013. He is a reviewer for more than 20 high impact factor journals, including the Journal of Biotechnology, Corrosion Science, International Biodeterioration and Biodegradation, Chemical Engineering Journal, as well as Water SA. He has also served as a member of the scientific committee at the Euro-Mediterranean Conference for Environmental Integration for several years. He constantly reviews funding proposals and grant applications and rating applications for the NRF, WRC, and MRC. Professor Lin has been an invited speaker at several international conferences in the United States, Singapore, Taiwan, and South Africa, among others. He was a visiting scholar to the Institute of Biological Chemistry in Taipei in Taiwan in 2010, and he was appointed as an adjunct professor at the Jiangsu Academy of Agricultural Sciences from 2015 to 2020. He is currently a C2 rated scientist by the National Research Foundation of South Africa since 2007. Professor Lin, congratulations on your academic achievement, and we all look forward to your inaugural lecture on the interesting topic, saving the environment using the little things. You can now go ahead and please present your lectures, Professor Lin.
Sorry for all the messed up. Okay, good afternoon. First of all, I would like to thank Professor Modi and Professor Orlando for their kind words of introduction. I also wish to acknowledge my family, my colleagues, friends, for supporting me on this journey. As soon as I start to prepare my presentation, I remember the acknowledgement in my PhD thesis, which I wrote 30 years ago. And it seems appropriate for me to share with you again now. So I always remember the article, Thank God, written by one Chinese scholar. The real meaning of thanking God is to thank those people who stand behind the success. All the effort and due to all the effort by different people from different levels and make success possible. People enjoy what they do. They want to express their appreciation to all the known and unknown people. Therefore, they choose God to express their thanks to everyone. I also am thankful to God, grateful to the wonderful life, so for the wonderful as well, that I have always had. I feel appreciated and also appreciate all the living creatures, the universe, for the magic. That's for the backup system, what we messed up, when we messed up. My journey of life started 60 years ago as a 6-month premature baby, protected by the first incubator, which arrived in the hospital at the right time. The medical staff wanted to give me up, but my parents believed that no cost was too much to save me. My parents would spend 1 month of salary for my 1 day of treatment. My brother and my relatives love me always, and I have a very good childhood with joy through the primary and junior high school. I complete schooling at one of the top high schools and the university in Taiwan. In fact, I spend a lot of my focus on the extracurricular activity and led the harmonica orchestra, as you can see the photo, as a conductor. It was another joyful period in my life. My academic interests were ignited during my final undergraduate year. I joined a research lab and felt this profession suited me well, and I decided to develop further in this field. I spent 2 years in the Army and 1 year as a research assistant at the National Taiwan University before being offered a scholarship for my PhD degree at the State University of New York at Buffalo, and mentored by Professor J.H. Wang, who was an Einstein Chair Professor of the New York State. After earning my PhD, I was invited to complete postdoctoral work at Yale University by Professor Coleman. During my graduate study, I met one of the most important persons in my life, my wife, and decided to move to South Africa, which is her hometown, home country. So after my postdoctoral work, my first job in South Africa was as a senior research associate with Professor Pillay. As shown in this photo, you can see my first academic family in microbiology in South Africa. Professor Chen Yang, Dr. Govindan, Professor Swansky from DUT, and many others. I managed to publish 2 peer-reviewed papers based on my research results in this period. In 1997, I was thankfully offered a lectureship at the University of Zululand. The Department of Biochemistry and Microbiology was not research-oriented at that time. We had only 3 incubators and some reach in the whole microbiology. Just a week after I joined the University of Zululand, Professor Cyrus, the zoology department, invited me to join his funding application. For God's grace, my component of water research of the project was awarded 1.4 million for 3 years from the National Research Foundation. At the same year, the funding was used to develop the research infrastructure in the department and yield more than 15 peer-reviewed publications in water research and the collaboration. I also managed to secure more funding from the Medical Research Council for the Zulu traditional medicine and TB research. One paper published in the Journal of the Pharmacologist was the #2 highest citation in that journal in that publication. In 2002, one of the major oil spill incidents in South Africa took place in St. Lucia estuary, resulting in the closure of the Amflodi River to prevent the diversity disaster in the St. Lucia estuary. So I asked myself, can we do anything about this kind of pollution as a microbiologist? The safest way of detoxification of pollutants is bioremediation. The bioremediation is the use of either naturally occurring or deliberately introduced living organisms or microbial bioproducts. That can be bacteria, can be fungi or plants, to remove or break down environmental pollutants in order to clean a polluted site. Bioremediation is only effective where microorganisms can grow and thrive. It usually requires the manipulation of the environment, such as the addition of oxygen, nitrogen, to allow the microorganisms to grow optimally and degrade the pollutant at a quicker rate. Immobilize the contaminant through nature-occurring biogeochemical process. The biogeochemical process can take place in almost all the environment positions on Earth because of the adaptability of the microbiome. It is important to know that bioremediation uses no toxic chemicals. In order for bioremediation to be efficient, microbes must transform pollutant as the carbon and energy source into non-toxic product, which is important. Providing an optimal environment condition to allow microorganisms to grow faster and then degrade pollutants at a quicker pace. After the bioremediation process, these microbial populations will decrease due to the disappearance of the pollutant. One of the most significant petroleum disasters is the Exxon disaster in 1989. Most petroleum hydrocarbons are biodegradable under aerobic conditions. So the petroleum contaminant could be degraded by the additional microorganisms. However, the biodegradation process was extremely slow due to the cold weather in Alaska. The major concern was also in the contaminated short. So a biostimulation process by supplementing fertilizer in the exon spoke was applied, adding slow release fertilizer containing nitrogen nutrients extensively can boost up the oil degrading indigenous population to speed up the rate of oil degradation. The result demonstrates that biostimulation increased the rate of polycyclic aromatic hydrocarbon degradation, or the PAH, by the factor of 2 and of alkyne by the factor of 5, relatively to the control in non-biostimulated site. The exxon spill is the first example in the petroleum spill disaster using bioremediation techniques. Another famous example of bioremediation is the deepwater horizon oil spill in the Gulf of Mexico in 2010. In this case, a thick oil slick was formed in the ocean. Most petroleum hydrocarbons are highly insoluble in water. Therefore, hydrocarbon degradation mainly occurs at the oil-water interface. Thus, the surface area to volume ratio of the oil can significantly impact on the biodegradation rate. Dispersants such as Polydent 9500 was added to the polluted site. They increase the available surface area and increase the rate of degradation. Dispersants break down the oil slick into the smaller droplets that more readily mix with the water. Dispersants do not reduce the amount of oil entering the environment, but push the effect of the spill underwater. Metagenomic analysis techniques become available before the deep water horizon spill, unlike the Exxon incident. Many studies show that natural succession of oil degrading bacteria are found in the oil spill. Bacteria like Pseudomonas, Coelia species will dominate in the early oil biodegradation in the deep water horizon spill, and the Flavobacterium species and others subsequently involved in the degradation process. So lesson from these two oil spills and many others has already clearly demonstrated that despite different treatments used to remove or disperse the oil, the unseen nature suspected microorganisms were largely responsible for the disappearance of the spilled oil. Therefore, the nature of the oil degradation microbes played a major role in the environmental protection. Before I could start the bioremediation project at the University of Zululand, I received an offer of an associate professor in this department in 2003. Due to the family reason and a better infrastructure here, I decided to move back to this familiar environment. The photos show my parents' visit to the microbiology department at the E1 block. At that time, Professor Pillay and I were the only permanent staff member in the department. By God's grace again, I received more than 1 million research funds from the National Research Foundation and the University in 2004 to initiate bioremediation of industrial pollution projects. And I put a lot of focus on the bioremediation of the petroleum and the chlorophenolic compounds. Therefore, in this lecture, I'll pay more attention on petroleum biodegradation. We collected used engine oil from a Mercedes dealer and isolate the efficient engine oil degrader from the local contaminated soil. 3 dominant species were isolated: Pseudomonas species, Acinetobacter, and Faber-bacteria. These 3 isolates were also found as the dominant species bacteria in the deep water horizon slope. The results show that from the figure, the Acinetobacter could degrade 2% used engine oil up to 84%, followed by 71% by Pseudomonas species in 2-week incubation period. The consortium of all 3 isolates speed up the oil degradation to 91%. So the studies demonstrate that some local indigenous microorganisms have adapted to the oil contaminated soil and possess efficient biodegradation capacity. The consortium was working better than the individual species. We also evaluate the effect of fertilizer supplementation on diesel degradation in the contaminated soil, including long soil, sea sand, and clay. The result through the concept of biostimulation in the exon work, that supplementing the local fertilizer could speed up the diesel biodegradation by the indigenous organism. The effect of biostimulation depends on the soil type, nutrient added, and the indigenous population. In this study, the biostimulation did not work well in clay soil. Similar approach applied to the diesel biodegradation. Mean microbed would isolate from the diesel contaminated soil, augmenting bacillus isolate to a contaminated soil could speed up the diesel biodegradation together with the indigenous population. You can see the slide in the figure. In addition, biostimulation by adding local fertilizer also work well. The SEM image shown on this slide further show that the fungal population might also involve in the process of diesel degradation as their population increase during the degradation. In dewatered horizontal oil spread, dispersant was used. Many oil degrader also produce biosurfactant with similar properties. Therefore, many grain-passing bacteria were isolated from the artificial diesel degraders, diesel contaminated soil. As you can see in the figure, all isolated show good capacity for peliform degradation, but possessed different ability to degrade diesel. The level of diesel degradation correlated to the biosurfactant production, as you can see in the table. The results show that bacteria biosurfactant could function like dispersant using the seawater horizontal film. They increase the surface area to enhance the degradation rate. So we can see that the Mother Nature has the solution already. In fact, different types of biomolecules, such as bioflocculant, produced by bacteria, can also be used in the environmental treatment. The slide shows that bioflocculant produced by bacillus, bacillus, would remove organic and inorganic compounds from the industrial effluent. Bioflocculant remove almost all the bacteria and reduce 50 to 80% of the turbidity of a chemical effluent sample simultaneously. The produced bioflocculant also were capable of removing many heavy metals from industrial effluent simultaneously as well. Therefore, bacteria bioflocculant provide alternative means of treating industrial wastewater, resulting in environmental benefits. The presentation so far is trying to show that Mother Nature is saving this earth all the time using the little things, bacteria and fungi. Even when disaster strikes, we can learn from nature by using biostimulation, bioaugmentation process, or both, to speed up the remediation. During our study, we found out that biosurfactant can be used to many different applications based on their characteristics. Biosurfactant can be used not only in the petroleum industry, such as microbial enhanced oil recovery, and in environmental applications such as bioremediation and biodispersal. They also can be used in food processing industry, food safety, cosmetic industry, and many, many more. Therefore, in recent years, we have tried to explore the potential of Acinetobacter B2 and Pendibucillus B9, what they produce, biosurfactant they produce. To use biosurfactant as a tool and make it economical, the production and yield had to increase. As you can see in this slide, Acinetobacter B2 can only produce 0.58 grams per liter of biosurfactant at the very beginning, use the coconut oil can increase the yield of biosurfactant production to 1.97 grams per liter. The biosurfactant was purified and identified as the lipopeptide. It is stable, thermostable up to 100 degrees and pH stable. Based on this characteristic, this biosurfactant can support application in cosmetic and laundry detergent formula, which will be tested in the future. The V2 biosurfactant demonstrates the ability to remove heavy metal, similar to synthetic surfactant SDS. You can see the bottom figure and the table. They can remove the heavy metal from the contaminated sample and from the contaminated vegetable. In addition to degrade the used engine oil, Acetylbacter B2 can also break down the 0.4 gram per liter of phenol in 24 hours. Using a stepwise continuous acclimation process, the V2 increased the phenol degradation ability to 1.4 grams per liter in 1 day. It also enhanced the biodegradation of aniline, phenolate, and toluene to the similar level simultaneously. The industrial effluent from the local raising company contained the phenol concentration at 32 grams per liter. Therefore, low capacity of Acetylbacter B2 to remediate this industrial effluent is not cost effective. However, one bacteria strain Pseudomonas isolated earlier in my lab was found to degrade phenol at 3.2 grams per liter. Unfortunately, this strain was lost due to the load shedding related malfunctioning in biofreezer in the past. Acetylbacter would also be used to rejuvenate the aged insulating paper used in transformers. The bacteria strain was more superior in maintaining the paper structure and quality compared to the used chemical treatment like sodium hypochlorite and hydrogen peroxide. So this bio-bleaching process using V2 to rejuvenate aged insulin paper could reduce the pollution. Biosurfactant produced by Pendibucillus was also studied. The optimal production was increased to 4.11 grams per liter from 1.1 grams per liter by changing different experimental conditions. For example, they change the substrate and they change the carbon-nitrogen ratio and the incubation time and the amount of incubation. So D9 biosurfactant is also stable in temperature up to 120 degrees and stable in the whole period of the whole range of pH, as well as can tolerate higher salinity. It was more effective in reducing surface tension and increasing emulsification compared to non-anion synthetic surfactant twin AT. The D9 biosurfactant was also purified and identified as a lipopeptide, which is similar to the one by V2. The previous study showed that penibacillin D9 can degrade 70 to 80% diesel at the 2% concentration after 4-week incubation. However, the same bacteria strain only degrade 24.5% diesel at 10% concentration. With increasing biosurfactant concentration before the degradation, penibacillin D9 managed to degrade up to 65.1% diesel under the same condition, and synthetic surfactant SDS failed to demonstrate the same property. So the result clearly demonstrates that D9 biosurfactant increase the oil surface area and enhance the diesel degradation. Therefore, D9 biosurfactant can be applied to hydrocarbon flow. Use the canola and the sunflower oil, increase the yield of D9 biosurfactant to 5.31 grams per liter to 9 grams per liter respectively. It's already almost 9 times from the very beginning. As shown in the table, D9 biosurfactant also show a superior performance in the microbial enhanced oil recovery and the oil dispersion assay compared to the synthetic SDS and Trinton X100. The effect of biosurfactant is due to the higher capacity to reduce the surface tension and the formation of steady emulsion. D9 biosurfactant was capable of removing almost 100% of many heavy metals simultaneously, except magnesium, from an acid-minus vantage effluent from Richards Bay. This is important to know that the pH value of the effluent changed from pH 1.17, which is very toxic, to pH 6.0 after biosurfactant treatment, which is close to the natural condition. Similar to Acinetobacter B2, penibacillin D9 can effectively remove heavy metal from contaminated vegetable and from the contaminated sand. Therefore, D9 biosurfactant also show the potential food safety and environmental protection. D9 biosurfactant was tested for its fabric washing ability as a detergent, even though the washing performance of fabric stained by the tomato sauce and coffee were not better than the commercial detergent. As you can see in the figure, D9 green color, light green. But a 1-to-1 mixture with the detergent and D9 biosurfactant improved the wash performance. Equally important, D9 biosurfactant show no or minimal toxic effect based on the phytotoxicity test and the Bryan-Shinn test. Therefore, D9 is safe to use in field study and in situ remediation process. So in order to promote the biosurfactant application, the production is crucial as what I mentioned earlier. 20% D9 initiate diesel degradation by release successive enzymes such as alkyne hydroxylase, alcohol dehydrogenase, aldehyde dehydrogenase before the beta oxidation process. Remove 2 carbon lengths. The remainder intermediate continue to go to the cycle of degradation process. The biosurfactant, however, can be synthesized by the carbohydrate degraded intermediate and short peptide generated by non-ribosomal peptide synthesis. They join together by SFP enzyme, which is an esterase. Is it possible to improve the biosurfactant production by expressing SFP gene by a recombinant E. coli? Try it out. So recombinant E. coli containing SFP gene was successfully generated and expressed. So recombinant E. coli exhibit an improvement in the biosurfactant yield, 1.11 grams per liter in 24 hours, compared to 0.52 grams per liter by Pseudomonas D9 under the same condition. Therefore, the cloning can be a tool to optimize biosurfactant production. The biosurfactant produced by the recombinant E. coli can also reduce surface tension like what D9 biosurfactant did. High esterase activity was also observed on the recombinant state. Cheaper carbon source such as used canola, sunflower oil could also induce the biosurfactant production using the E. coli recombinant state. However, the biosurfactant produced by E. coli strain show different patterns of FTIR with the D9 biosurfactant. Therefore, the E. coli recombinant strain might not produce the same biosurfactant as the 20% of the time. So overall, the microbial biosurfactants from D9 and B2 are environmentally friendly, non-toxic, ineffective to enhance the bioremediation of oil components, and can be applied to many other industry applications. The future research will try to apply the exact knowledge in field study or in situ application. We would also attempt to fully elucidate the structure, composition, characteristics, and quantification of biosurfactants produced by these super producing strains under various conditions. Finally, it's important to share some exciting developments in the bioremediation of plastics. My feeling is it will provide some direction for our new research. Plastic has been produced in 1940. Now plastic pollution represents a global environmental crisis. Plastic comprises 12% of solid waste, of which less than 10% has been recycled. And plastic debris in the environment has become substrate and a new niche that microorganisms can colonize, already forming the so-called plastic sphere. Plastic pollution is shaping microbial community in the environment through adaptation. One bacteria strain, Inaugural 201F6, was isolated from a plastic waste site in 2016 in Japan. This Inaugural strain contains PETS enzyme that can biodegrade plastic. The original strain could only degrade one plastic bottle in 58 days. So scientists have cloned the gene into E. coli. So after cloning, the enzyme degradation ability has been significantly improved through the computer modeling, as you can see that, or the key amino acids of the enzyme has been modified, mutated to increase the ability to degrade the plastic. The recombinant PETS enzyme now can degrade the one plastic bottle within 24 hours. And the enzyme can degrade more than 30 different plastic products available in the supermarket. Therefore, we should be aware of the impact of the molecular biology or molecular technique, modeling, artificial intelligence, and all this cloning, mutation in our future study. Nature is the most amazing recycler. It contains numerous gene pools within bacteria and fungi to address any potential environmental disaster, such as plastic and so-called forever chemicals. With adaptation, evolution, the microorganisms capable of degrading pollutants will emerge and be discovered through the microbiological technique. The molecular technique mentioned previously can improve the biodegradation properties significantly, as the case of plastic. Pseudomonas species 273, which can degrade forever chemical with the first polyfluoroalkyl substance, have a very similar property like a plastic, even more difficult to degrade. Has been isolated. This year, we can expect many progress will be observed in the very near future. In fact, the best method to save the environment is to stop pollution. However, this is impossible in today's climate. What we can do is to develop the tool to speed up the biodegradation process and to minimize the impact of pollution using these little things, bacteria and fungi. Finally, I want to express my appreciation to my mentor, Professor Wayne, for his guidance, showing me what a real scientist is. At the age of 80, he was still working on the bench for his research. I will also thank all the people who have been important and collaborated in my research. There are many more people who have touched my life that are not showing this life. Lastly, our biotechnology cluster, as well as my family. Thank you all for listening and attending this presentation. Thank you.
Wow. Thank you very, very much, Prof. To say that was food for thought is an understatement. What a topical question that is filled with many questions regarding the challenges of the world today. And I'm sure I'm not the only one who says that if you were listening carefully to this presentation, you learned a lot about how you can help the world to be a better place when we are facing the challenges of pollution, the challenges of climate change that are also linked to other challenges that affect our lives in a very negative way. But we are grateful that we still have people like you, and we will look after you at UKZN. We did not make a mistake by making you come to UKZN. We congratulate you for agreeing to stay here and to climb up the ladder to be our full professor. We look up to you to assist us to mentor young people within and outside of UKZN to take this particular area of study forward and make our university to occupy the position that it deserves in terms of the world rankings. Of course, I would like to also repeat thanks to everyone who supported you, your collaborators, research collaborators, your students, but most importantly, your family. Thank you very much. And the people who gave us this opportunity to listen to you are very special people. You don't get a chance to listen to our excellent professors. So our PR division, well done. Keep doing the good job of presenting and bringing the scientists to us. Thank you, colleagues. So Pam, are we free to fly?
Yes, Prof.
Thank you.
It is
Well
the
done.
end of the lecture, and thank you so much, and well done, Professor Lin. Thank you, and thanks, Professor Ade.
Thanks,
Thank you
Pam.
to
Thank
everybody.
you all for your assistance.
You-
Sorry
Thanks,
for the
everyone.
trouble.
Yeah.
Thanks, Sally.
Congrats once
Thank
again,
you.
Prof. Lin. Good luck.
Bye.
Thank
Thank you.
you.
Bye-bye. Thanks, Prof. Bodhi, for your time.
Thanks, Ade. Well done.
Okay.